The 2026 AIME problem 14 is an excellent problem combining both geometry and algebra techniques. Golden ratio and golden triangles are also heavily used in the solution. Let ABCDE be an equiangular pentagon. All five angles have the same measure of 180 degrees. The sum of the squares of five sides equals 308. The five sides are A, B, C, D, and E. Its five diagonals have lengths A1, B1, C1, D1, and E1. The sum of their squares equals 800. Question: what is the square of the perimeter of the pentagon? A quick calculation. The square of the perimeter includes two parts. First, the sum of the squares of the sides. Second, 2 times the sum of pairwise product of the sides, total 10 products, AB, AC, AD, AE, BC, BD, BE, CD, CE, and DE. The first part is equal to 308. We will be working on the sum of the 10 terms. Shrink the graph a little bit, and then extend the size of the pentagon to create 5 triangles outside the pentagon. Because the interior angles of the pentagon all have the same measure of 108 degrees, their exterior angles are 72 degrees. So we just created 5 similar isosceles triangles. Their angles have 72, 72, and 36 degrees. These triangles are known as golden triangles. They will play a key role in the solution. Let's spend some time to review the properties of golden triangles. Assume a golden triangle XYZ has a base with side length 1. Its legs XY and XZ have length 5. Let YW be the angle bisector at the angle Y. Then the angle Y is partitioned into two angles with 36 degrees. Therefore, triangle YZW is also a golden triangle 36, 72, and 72. Moreover, the triangle WXY is also isosceles with two base angles 36 degrees. Then YW equals YZ, which is 1, and also XW equals YW, also be 1. Because XZ have side length phi, then the remaining part WZ is phi minus 1 here. Now, we have two golden triangles, XYZ and YZW. They are similar. The similarity ratio can be calculated by leg to leg, that is phi to 1, or base to base, that is 1 to phi minus 1. Then we have a quadratic equation in phi. Phi squared minus phi minus 1 equals 1. It has two solutions, one positive and one negative. The positive one is the real value for phi. Indeed, it is the golden ratio, 1 plus root 5 divided by 2. Golden triangle can also be used to calculate values of trigonometric functions of some special angles. Apply law of cosine on triangle XYZ at the angle X. A 36-degree angle. Its opposite side has side length 1, so 1 squared equals phi squared plus another phi squared minus 2 times phi times cosine of 36 degrees. We can solve for cosine 36 degrees. It is 2 phi squared minus 1 divided by 2 phi squared. Split the 2 phi squared on the top into two terms, phi squared plus phi squared. The second one minus 1. According to the quadratic equation for phi squared minus 1 is simply phi. So phi squared plus phi divided by 2 phi squared. Take out phi on the top, we have phi plus 1. Again, according to the quadratic equation, phi plus 1 is simply phi squared, phi times phi squared. So cosine of 36 degrees is simply 1/2 of the golden ratio. To summarize, golden ratio is 1 plus root 5 divided by 2. More importantly, it satisfies a quadratic equation phi squared equals phi plus 1. Also, cosine of 36 degrees is 1/2 of the golden ratio. The third one for cosine can be used to derive cosine value of 108 degrees. Cosine of 108 degrees is cosine of 3 times 36 degrees. Then we apply triple angle formula for cosine. It is equal to 4 times cube of cosine 36 degrees minus 3 times cosine 36 degrees. Plug in the value. We have phi cubed. Phi cubed can be split into two terms, phi times phi squared. And then we know phi squared will be phi plus 1. Multiply them out, we have another phi squared. It is phi plus 1 again, and we end up with 1 minus phi divided by 2, which is a negative number. Let's go back to the AIME problem. We have 5 golden triangles. Their bases are A, B, C, D, and E. Therefore, their legs are phi A, phi B, phi C, phi D, and phi E. We are ready to calculate the sum of the pairwise products of the 5 sides. We start with triangle ABE. Applying the law of cosine on this triangle at angle A. Angle A has a measure of 108 degrees. Its opposite side, BE, is a diagonal, have length A1. So A1 squared equals C squared plus D squared minus 2CD times cosine of the measure of A, which is 108 degrees. We already know 108 degrees is 1/2 of 1 minus 5 and times 2 here. Now we have a product CD of two sides. We want to solve for that. Phi minus 1 times CD equals A1 squared minus C squared plus D squared. Multiplied by phi on both sides. The left side is phi squared minus phi. According to the quadratic formula for phi, we know phi squared minus phi is simply 1. So 1 times CD equals phi A1 squared minus phi times C squared plus D squared. We can use similar approach applying the law of cosine on the other nodes B, C, D, and E. We got another 4 equalities for DE, EA, AB, and BC, and then sum up. The sum of 5 products of sides AB, BC, CD, DE, and EA equals 5 times the sum of the squares of 5 diagonals minus 2 times the sum of the squares of 5 sides, as each side appears twice here. We know the sum of the squares of diagonals is 800. I denote it as alpha for simplicity, and the sum of the squares of the sides equals 308, denoted as beta. These are the 5 products of neighboring sides, AB, BC, CD, DE, and EA. There are another 5 terms, AC, BD, CE, DA, and BE. They can be evaluated in a different way. Consider triangle AQT. It is an isosceles triangle with two 36-degree angles. Then AQ is congruent to AT. AQ is C plus phi times B, and AT equals D plus phi times E. Rearrange the term. C minus D equals phi times E minus B. Square both sides and expand. Now you will see why I do this calculation. On the left-hand side, we have C times D. This is a product of two neighboring sides. And on the right-hand side, E and B are not neighbors. Perform similar calculations on the other 4 similar triangles and add them up. On the left-hand side, we have 2 times the sum of squares of the sides, which is 2 times 308, or beta, minus 2 times the sum of the squares of the neighboring sides. Right-hand side is similar, but everything is multiplied by 5 squared. And we also have AC plus BD plus CE plus DA plus EB. This is the last piece we need to find. We move this piece to the left side and everything else to the right-hand side. We already know the sum of 5 product of neighboring sides equal to alpha minus 2 beta. Plug it in and simplify it. It is equal to phi times alpha minus beta. So phi squared times the sum equals phi times alpha minus beta. Therefore, the sum equal to alpha minus beta divided by phi, which is actually phi minus 1 times alpha minus beta. A quick check. 1 over phi. 1 is actually equal to phi squared minus phi, the quadratic equality for phi. Let's put all the pieces together to solve the puzzle. The square of the perimeter equals the sum of the squares of the sides plus 2 times the sum of pairwise products of the sides. The first part is beta. Those 10 products can be separated into 2 pieces 5 by 5. The first piece is equal to phi times alpha minus 2 beta. Another piece, phi minus 1 times alpha minus beta. After a simple calculation, we got 2 phi minus 1 times 2 alpha minus beta. Now, we are ready to plug in all the numbers. 2 times the golden ratio minus 1 is simply root 5. 2 alpha minus 3 beta is 676. Thank you for watching.